Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Laws of programming. I did publish an article in 1987 in the Communications of the ACM called Laws of Programming, and it dealt only with sequential programming. 1987, I should have known better. Could you come down to the front, please? I have to apologise for a weak voice. I think it's hay fever. Could you come down to the front, please? If you can't hear this, please come down to the front. Would you like to come down to the front, Peter?
I can hear you.
Thank you. Then I can speak more quietly. But just recently, that's probably about 5 or 6 years ago, I discovered how to construct a law for concurrency. And investigating it over the years, I found it is a remarkably powerful law, and those of you who haven't heard of it before might know it under the name of the exchange law, which is used in category theory. So, let's see what I've got. Summary. What are the laws? What do they mean? Are they useful? Are they true? And are they beautiful? Well, I'll leave you to answer the last question, but I hope to show you, or at least give you some evidence, that what the answers to these questions should be. What are they? Well, the laws are going to be algebraic laws of the usual kind, very similar to those you find in high school algebra, relating to numbers and arithmetic. They will contain free variables which are assumed to be universally quantified, and I'd like to give you some intuition as to what those variables stand for. The variables PQR will stand for specifications, designs, or programs. Descriptions of the behaviour of a program that we may have written already, or may yet to be executed in the future, or may be executing now. The descriptions may be used to describe the desired behaviour of a program, or the a planned behaviour of the program, that's in the case of a design, or the actual behaviour of a program, of a particular program which has been written and is executing past, present, or future. A single behaviour will be recorded as a set of actions which take place in or near a computer that is executing the program. Now, the algebra I will deal initially with 3 operators, then which stands for sequential composition, concurrent or with, which stands for concurrent composition, and the third one is a constant skip, which does nothing. It has no events in its execution, for example. Then P semicolon Q describes the behaviour which might result if you executed all the events in the execution of P and followed these by all events in the execution of Q. That, I think, should be one way of executing P semicolon Q if it's written in a program. And P with Q describes the concurrent execution of P and Q. It contains all events in P, all events in Q, and it starts when, but both executions start at the same time and end at the same time. So quite a familiar construct. It was introduced by Dijkstra. Now there will be 5 axioms to start with, the simple axioms. Both operators are associative. Both of them have the same unit skip, and concurrency is commutative. I hope your programming intuition will persuade you that those axioms are true, or if not true, then it would be an awfully good idea if they were true. Because that's what axioms are good at. They're good at specifying what you want of your language without telling you how to implement it, or how to implement programs in the language, or how to prove them in any way. They really are quite, one might almost say, intuitive. Now, since we've written these axioms down, we can note something about their syntactic structure. If you take any of those axioms and you reverse the operands of all the semicolons in it, you will get another axiom in that same structure, another axiom in the same group, or possibly even the same axiom. This means that if you're using only these axioms in a proof, and you perform the reversal on every line of that proof, all the axioms will remain axioms, and all the deductions will remain valid when you substitute equals for equals in an algebraic proof. So more formally, we can use a meta-theorem, known in the computer science community as theorems for free, which says that when a theorem is translated by reversing the operands of all the semicolons, or of some of the concurrent operators, the result is also a theorem. This is a sort of time reversal symmetry which our axioms so far obey, similar to the time reversal symmetries that you find for many, but not all, the laws of physics. Now, the concept of ordering or refinement, I'll use just an ordinary implication arrow to stand for a refinement, which means that every execution described by the left operand of the implication is also described by the right-hand side. It's very similar to implication, where all models of the left-hand side will be models of the right-hand side. In other words, if P is more predictable and more controllable than Q. Now, if P is a program and Q is a specification, then we can use refinement for just correctness of the program in accordance with the specification. If both of them are designs, it means that the design on the left adds more decisions, is more constraining on the behavior of the design than the design on Q. So we can use this refinement relation in the standard way to justify a chain of steps in the development of a program. Now, axiom. Refinement is a partial order. This is really essential for the stepwise refinement method to develop programs. We can note a duality principle again, that with these axioms, swapping the operands of refinement translates each of the axioms into itself. And this justifies a duality rule by order reversal. If P refines Q is a theorem proved from the axioms, would that be true? So is Q arrow P. Should I pass over that just rather quickly in case it's wrong? It's not really essential. The concept of monotonicity should be very well known to all mathematicians. Anybody claim to be an engineer and not a mathematician? Great. In that case, you may not have heard of monotonicity, but you use it every day when you've designed a product out of components, and somebody comes up with a better version of one of the components that you've used. You replace the original by the better one, and as an engineer, would you expect your whole assembly to be better or not? I said better, and by better I meant better in all respects. It lasts longer, it's cheaper, it's faster, it uses less power, everything. It's better. Because that's what we've got to mean by refinement. We want to forget all those respects in which something might be better and just use the betterness of it to justify replacement of an existing component by a better one. I would claim that if you found, as indeed engineers quite frequently do find, that installing a new component does not make it better, that means that the original design was based on a theory of physics, or whatever, electronics, which was incorrect. It should not, it's based on some principle which does not preserve monotonicity. So monotonicity has a very important engineering implication, as well, of course, as being the fundamental concept in mathematics. Yes?
I take it you're going to introduce plus sometime later, right?
I'm going to introduce plus sometime. Let's wait and see.
The only question being, why do you make the thing in the middle axiom, since it'll probably be a theorem later?
Everything I've told you so far is an axiom. And all my hand-waving is just an explanation of why you should want it to be true. I will... the question that you have asked is equivalent to the question, is it true? And in order to show that it's true, we have to construct a model and prove the axiom. So it's like in other mathematics, one man's axiom is another man's theorem, and that's a very nice relationship. So monotonicity, this is a better theorem, of course, allows the replacement of a term in an expression by a better one in all contexts. And that's just a statement of this fact that is very, very commonly used in mathematics and even in algebra. So let me introduce now the one. Yes.
Go back to the last one that you didn't have a chance to read it.
No, don't read it.
Oh.
I've already told you. And besides, it might contain a mistake, but I think you all understand. The exchange axiom. This is the new one, which I sort of, usual scribbling around, exploring various things. You suddenly write something down, and wow, it seems to be true. Then later on, one discovers that it's actually useful as well. The exchange axiom is an axiom about concurrency. It's slightly difficult to make it intuitive. And the reason why we want it, I'll come on to the reason why we want it to be true when I describe how useful it is. But intuitively, you could say that the left-hand side is a more interleaved version of the right-hand side. It makes a decision as to how to schedule the behaviour. If you look at the right-hand side, it has two threads. The left-hand side makes a decision on how those two threads are to be scheduled. It says that the two displayed semicolons on the right-hand side are to occur together. In other words, all the events in P and Q are to happen before any of the events in P dashed and Q dashed. So we've got a semicolon on the left-hand side it separates the events from P to P dashed to Q to Q, from Q to Q dashed. The two semicolons have been aligned with each other in time to ensure that only a subset of the interleavings will be true. It's slightly confusing because it may be that the left-hand side is actually undefined and it has no executions. But that will be the secret of the validity of this law in circumstances where we have the possibility of deadlock. If no, that's going a little bit deeply for this stage. We need to have a look at a model to explore how the left-hand side can be undefined, whereas the right-hand side is defined. If there are inputs and outputs between P and Q, then the left-hand side may be undefined in cases where the right-hand side is defined. Applications. Well, I would like to claim that the laws are useful. They're at least as useful as the laws of Hoare logic for the proof of correctness of programs, extended by separation logic to the proof of concurrent programs. Every proof of the correctness of program is an application of the laws that I have shown you so far. Now, almost certainly contains many applications of these laws. And the way I can prove that is to prove that the laws of Hoare logic actually follow from the simple axiomatic foundation that I've given you. I also recently discovered that the same is true of the laws of Milnor logic, of the operational semantics, which uses Milnor triples instead of Hoare triples to describe how programs should be executed. So again, although not all process algebras are defined by Milnor's principles, we can derive from the laws a version of an operational semantics of our language, which looks useful in defining particular executions of the programs. So the operational semantics tends to be used by implementers or anybody who's looking for a particular execution of a program, whereas the proof rules are used by people who want to make generalizations about all programs having a certain property. So, in order to prove the laws of Hoare logic, I've got to define the primitive judgment of Hoare logic, which I do in this simple way. The triple is defined just as a simple refinement between a sequential composition and and an arbitrary program. So if P describes what has happened so far, and Q is then executed to completion, then the overall behavior of P and Q together will be a refinement of R. Now, in traditional Hoare logic, P and R are confined to be assertions. What I will have to somehow persuade you to accept, maybe temporarily only, is the idea that it doesn't matter replacing the P and R by arbitrary descriptions of the behavior of a program. For example, if you take a relational view about a program, then P could describe the behavior of the program from the moment that it started, and R could describe the program up to an arbitrary but fixed moment in the future, or indeed for infinity, or infinity backwards. So the Hoare laws are really special cases of the general laws which are derived from this definition. But I know that many people will find it difficult to swallow, the idea that one can reason in triples about programs, specifications, and designs. Yes?
Did you have any of this intuition when you were doing Hoare triples, or this is all about now? So were you thinking
all about now? No.
So you used to think of assertions and programs as different things?
Yes.
Yeah.
Yes. It was a mistake I made a long time ago, and a lot of people have been kind enough to make the same mistake with me. So, remember the definition. Look at the theorem of the axiom, the Hoare axiom of sequential composition, which I've written just below it. I claim that I can prove the validity of that law from the axioms that I've given you so far. There isn't much room on the rest of this slide, but I'll try just to show you. Oh, I won't, yeah. First of all, I'll expand the definitions. And then claim that using the monotonicity of a semicolon, I can replace that S by P semicolon Q. And because of the associativity, I have now proved the conclusion. That took me 30 seconds to prove. Have you ever seen a semantic proof that took 30 seconds? Before? I don't think I have. No inductions, no nothing. So what about the rule of consequence? I don't think the proof is much longer. It uses the same two properties, so I'll leave that as an exercise. You can take a minute and a half. Now, in concurrent separation logic, this is the modular rule for proving concurrent programs. It allows, if you have to prove the correctness of a particular kind of the conclusion containing a parallel composition, you can split that proof into two parts if you can split the two assertions into two parts and then prove the two parts separately. Now this is actually equivalent to the exchange law. So if you don't like the exchange law, but you do like separation logic, you're being inconsistent. They really are interderivable. Let's see. What we'll do is first we'll prove the modularity rule implies the exchange law. We look at the two assumptions of the modularity rule and turn them into theorems by making the right-hand side of the refinement the same as the left-hand side. Now, making the same replacement in the conclusion of the modularity law, we will get that implication there, which is just a statement of the exchange law. Okay. That's nice. So we now want to show that the exchange law implies modularity. So the modularity law has two assumptions, so we can assume that the antecedents of the modularity law and monotonicity of with gives us the implication, the refinement shown on the next line. Now the exchange law has a right-hand side, which is, if I've got it out correctly, the same as the left-hand side of this. And the left-hand side would look like this. And now by transitivity, we have the modularity rule. Okay, good. I hope you're thinking a little bit faster than I am, because I'm not quite following the proof as I'm saying it, but I know that Victor has. It's very comforting. So here we have some other important rules of separation logic. These follow from the frame theorem by just replacing one of the operands by skip. And because semicolon and a parallel have the same unit, these laws are just a simplification of the modularity rule. And it's interesting that we can find a Hoare rule which couldn't have been expressed if F and P were assertions, which has the same shape as the frame law. But the framing program F has to be the first operand of the semicolon. Okay, so I've left out all the basic statements. They need to be added. They are going to be expressed as axioms in the same way as in Hoare logic. So the rule of assignment carries straight over into a law of programming, as was described in the article in the communications of the ACM. The definition of the Milnor triple is really the same as that of the Hoare triple, with just the two operands reversed, the Q and the P. But it's read, it's interpreted in a different way. It says that R may be executed by first executing Q, the Q that's written in the middle of the line, with P as a continuation to be executed when Q is finished. So again, it's a refinement. There may be other ways of executing R than by executing Q first. You might execute Q dashed first and have a continuation P dashed, and they'd both be valid executions of the same R. Now, let's prove one of the basic laws of CCS, that Q then P may first do Q and then P. It is a tautology. And if you expand the definition, you'll see that it is a tautology. Now that's the rule by which CCS introduces the meaning of the prefixing action. In the standard CCS definition, due to Milnor, the Q has to be an atomic action. And therefore, Q has to be a single input or a single output. And that is the form in which Milnor quotes the law. But I'm using what Milnor called a big step semantics, in which I can allow Q to be, again, any program. So these restrictions do tend to stick in the throat of people who are familiar with the various kinds of logic, and that's fair enough, because in application, if you're applying our theory to real programs, you will in practice use something much more like Hoare logic, because it's specially designed for proving correctness. And similarly, if you're using the logic to guide an operational semantics or an implementation of the language, you will use an operational semantics, a presentation of the same laws. But for theoretical purposes, we want to bring these two studies together and show that they are consistent. Now, of course, acres of popple print has been expended on proving the consistency of operational and axiomatic semantics. And that's if you're lucky. Most papers will present only one of these two. My suggestion is that if you start with the axioms and make the intellectual generalization of not to distinguish assertions from program, not to distinguish basic actions from other actions, then all of these things follow from the same laws. And if the laws are true, I don't even have to say that, every model of program execution and behavior which satisfies the laws is also going to satisfy the operational semantics and the verification semantics. Period. I proved it to you. I've shown you. I haven't hidden anything.
You left the definition of parallel composition a little bit vague. You just said they run concurrently.
Yes.
But you didn't specify what kind of interference is allowed between the two parts of the parallel.
That's part of the model.
Pardon?
That's part of the model.
Right, so the equivalence of the exchange law to, I forget the name of the law in separation logic, I think depends on parallel composition being interpreted a particular way in your axioms, and that being the same as what separation logic says about the two parts of.
I and my colleagues, two of whom are here, Bernhard and Georg, have shown that there are enormous numbers of interpretations of these two semantics which make it work. So if it doesn't work for yours, try a bit harder. Thank you. Yes?
I have a slightly similar question. So you haven't shown us anything like a conditional statement, and I believe that's because that would be part of the model. Is that correct?
No, I can show the axioms for it. They are in fact shown in the communications of the ACM article.
So when you showed us this simple language where you have sequence and parallel, is that simplified for the purposes of this talk? Or
Yes.
Do you have other things?
I also have choice, union.
Okay, because my next question was going to be, can you have something like a conditional that on one branch does something concurrently? So the answer is yes.
Yes.
Yeah. Okay.
You can nest semicolon concurrency at will. If you really,
I got that
if
from
that-
sure. So
yes.
it's whether you could do more things with other constructs.
I do the same thing as Boogie, introduce an assume statement. Yes.
So I think the way that you stated it, it's sort of misleading in that you're being a little unfair to Hoare. Right. I mean, you make it sound that as if what's in Hoare logic is simply a special case of this, but of course it's not, because Hoare actually has incomparable axioms, right? There are models of Hoare logic which are not models of
Yes.
this. Right?
In fact, you can't derive the laws from Hoare logic or from an operational semantics. But if you do the derivation in the other direction, which has been done by Stefan, who's also here, you get a very large number of laws. It turns out that for Hoare logic, it's not necessary you can have a weak associativity law, in which which is just a refinement that I beg your pardon. The difference arises when we introduce choice, which I haven't done. In the case of Hoare logic, semicolon distributes backwards or forwards through, but not. I mean, through. but not the other way.
Without additional operators, simply the laws that you have, the fact that they already impose that the frame rule works, right?
The laws imply the two
Whereas,
specific
of course,
cases.
It didn't hold for the original Hoare logic, which means that it could prove some additional Hoare triples that wouldn't be true in
In Hoare logic.
right. So
Yes, that's right. I'll make it, that will be part of my summary. So I think as long as the axioms are consistent, really, if we talked about all the models of those axioms, then what I'm saying is really very strong. It doesn't say that, but it isn't an equivalence. The two calculi are definitely weaker than the laws. So here's a nice correspondence. I've proved for you the validity of sequential composition in the Hoare logic, and the law for sequential composition in Milnor logic is written just below it. Of course, Milnor didn't like sequential composition because you can define it in terms of concurrent composition. But if you do want to put sequential composition into a process algebra, this would seem to be a very reasonable big step law to do it by. If you look carefully, you'll see that one of them is just the time reversal of the other. So all those years when I thought that Robin Milner's semantics was a rival of mine, I was completely mistaken. We were arguing about which end of the egg to open first. Does time go forwards or backwards, as it were? And the laws are, as I say, insensitive to that distinction. Concurrency in CCS. The modularity rule, the exchange law, is also insensitive to time reversal, and therefore we can derive the concurrency law for CCS, which is just that, where P and P dash have to be restricted to particular basic actions, only if P and P dash are synchronized. It's just the time reversal of the separation logic rule. Frame rule for Milnor logic is exactly what he quotes as a rule for concurrency in CCS, that if a given thread can perform an action, it can perform the same action in any concurrent context. And the second rule is the dual of the frame rule for sequential composition, and that is the second thing you have to introduce into a process calculus in order to define the execution of semicolon uniquely. Yes, sorry.
Can I ask about the Milnor law for parallel on the previous slide?
Yes.
Can we go to that? So, see, the P and P parallel P primed, Milnor always required that they were opposite actions, like A and A bar.
Yes.
So, it couldn't be applied for arbitrary P and P primes.
That's right.
In a sense, it was a partial operation.
Definitely.
But here, parallel is a total operation. So,
I'm using a big step semantics, so it's sort of not quite so surprising.
Two non-opposite actions would be false.
it would be what?
False.
What's that?
What?
It doesn't exist here yet, does it?
That would not be consistent with these laws, I don't think.
X points to star, X points to X points.
Okay.
In the usual interpretation.
If you're looking for counterexamples, you should wait until you've considered models, which are much better at providing counterexamples than algebra. In fact, in algebra, you can't find counterexamples at all. So I think models and algebra have a very important complementary role in.
I think the question it had was whether this parallel composition is in fact an extension of Milner's, and the claim is that it's perhaps not.
Oh yes, the claim is that everything I say about Milner, I wish I could have checked with him. So it has to be a version of. So.
Also, excuse me, it is absolutely to do with big step v small step, because when you do small step and have the basic actions, then, for example, Robin's comment about that not having the sequential composition makes sense. You know, and it's because you've gone to the big step that these generalizations are coming up.
Yes, but if you look at my formulation of the sequential laws in the Milner notation, you'll see that when they even when those are restricted to just atomic actions on the arrows, that they are complete enough.
Yeah, no, understood.
Yes,
Yeah.
thanks. So, this is another time reversal sort of thing, a refinement reversal. And it's a sort of insight that on any step of execution, a computer can reduce the range of non-determinism of what it still has to do. Whereas in the case of a proof, on any step of a proof, the conclusion can increase the range of non-determinism of the antecedents. So it's just another duality. But when we consider the rule of consequence, we get a similar rule for the process algebra approach, which uses the fact that execution steps may refine the program that is being executed as a result of internal actions. And this law, again, I think, would not be acceptable to Milner, but it is to me, I'm afraid. Let's have a look. So, summarizing so far, both the Hoare and the Milner rules, the rules of the calculus, are derived from the same algebra of programming. The algebra is simpler than each of the calculi, has less operands, less clutter, and it's stronger than both of them combined. And more useful, for example, because we can use them very directly in optimization and in transformation of expressions, which, if we have a rule-based approach to reasoning, gets a little bit more cumbersome. So, at least in this sense, an operational interpretation, an operational semantics, and an axiomatic semantics gain a measure of compatibility, consistency, from both being derived by the same laws. It's not that there aren't models of the weaker laws. Of course there are models of the weaker laws which differentiate them, if that's what you want to do, but I want to unify them. So this is the way to do it. So I can't, shall we go on to models? What is a behaviour? I'm going to take a very general definition. In fact, I've already given it. It's a set of events occurring in and around a computer or a computer system that is executing a program. So the immediate interactions with the real-world environment of the computer system are also included as part of the behaviour. And that's really essential in order to model interactive systems. So let M be the set of all occurrences of all such events that ever were or ever could be. Ooh, that seems a little bit, why don't I, can't I construct them out of something? Why bother? Mathematics allows the existence of sets, and if I want to base my whole algebra, my whole model on the existence, I can parameterize my model by the set of events. I can decide later whether the events have a unique time of occurrence, whether they have a unique position of occurrence, whether they represent an assignment or an output or a fetch. All of these things can be decided later. All I need initially is a big enough set of events which act as a sort of carrier set of the algebra, and on which I can parameterize the syntax of my language and the semantics of the basic commands of the language. So remember, they are occurrences, two events. Two occurrences are always different. So I'm now going to introduce, I say, it's already appeared in many of the talks in this workshop, the concept of causal connection between events. Certainly used quite a lot in the lectures on weak memory. It's also used at a higher level in computer science when you deal with message sequence charts or Boolean waveform diagrams, where engineers draw an arrow between two events, i.e. rising edge or a falling edge, if they are intended to be causally connected. And here are some examples in ordinary software. The nth output on a reliable channel has the nth input on the same channel dependent upon it. The nth release and the nth acquire, the nth assignment and a read of the value assigned by the nth assignment. And in strong memory, the read of the nth value assigned by the nth assignment happens before the n plus first assignment. In a weak memory, that link has been broken, and you can read things that were written. Sorry, they could be broken. I think in future weak memories it will be broken, because future memories will be too slow, just too slow to make it possible to even give the guarantees that current weak memories give. So let's take the reflexive transitive closure of a dependency relation, which is the sort of direct or indirect necessary condition relation for some event to happen. And we take its converse in the usual way. And examples are that every allocation of resource must transitively precede every use of it. And every disposal of a resource must follow every use of it. In fact, if you really are defining the language by describing what the really essential condition on allocation and deletion is. Those two statements define allocation and release. They don't tell you how to do a memory allocator, but whatever memory allocator you do should satisfy that property. Now, we can interpret these symbols to explore the expressive power of our model. We can say that if E comes before F and F happens before E, since happens before is reflexive, it's not inconsistent. It's just that they must be the same atomic action. Conversely, if neither of these two dependencies occur, then the two events are independent of each other, and they can occur actually concurrently. Or one of them can occur before the other, or vice versa, or they may overlap in time. The model hasn't said what the interpretation of it is, but we can see how expressive the model is in saying the sort of things we want to say about events, even if they're not atomic.
Excuse me.
Yes.
Sorry, I've lost that top one about being atomic. I'm finding myself staring at it.
An atomic action are parts of the same atomic action.
E happens before F, and F happens before E, so they happen at the same time.
Maybe. This is only an example of the kind of intuition that you might have. So that's,
Yes, no, yes, okay. Thank you.
I think you may have some better intuitions, actually. Let's talk about possible traces or sets of events, P, Q, and R. And I can define P times Q as the Cartesian product of P and Q in the usual way, and prove a little theorem that a Cartesian product distributes through union. I haven't introduced union yet. And now I want to define sequential composition. This is just one of the ways of defining sequential composition, and I'm working on general recipes for defining other versions of sequential composition, if that's what you want. Let's introduce a relation, arbitrary relation, which I call sec, sequence, a relation between events. And I'm going to define my sequential composition operator in this slightly peculiar way. It's just the union of the events that occur in P with the events that occur in Q. So, do you want me to finish? There's nothing else scheduled. Thanks. Right. I'm defining a relation now between traces, which states that either P is undefined. This is the Scott definement ordering between traces. Oops. This one is the Scott definement ordering between traces, because I'm going to want the semicolon to be undefined in cases where this is false. So this says if you take an arbitrary event from P and an arbitrary event from Q, they will also be in the sequencing relation. So okay, let's go on. We want to prove the associative law from just the definition. We've left the actual definition of SEQ as a parameter of the model. You can get different versions of semicolon by filling in that parameter in different ways. So here is a proof that no matter what the relation you fill for SEQ, you will define an associative operator. So the LHS is defined if all the operands on the left-hand side are defined. So SEC must hold between the events of P and Q, and it must hold between all the events of P and R and all the events of Q and R. That's expressed by the fact that we can distribute the times through the OR. And when we do that, we can prove that the right-hand side is defined as well. I don't think it's worth spending any more time on that proof, but that's the length of the proof. Now, some particular examples that might be interesting for sequence. P semicolon Q could be the negation of the converse of the dependency relation. It says that no action of the first operand depends on any action of the second operand. Well, if it did, then you wouldn't be able to complete the first operand before you started the second operand, because execution of the first operand, completion of the first operand depends on something that is only available to you after you've started the second operand. So this seems a very weak definition of sequential composition, and for that reason it's very nice. For example, it does describe the way that sequential composition is implemented on this machine. After optimization. And here's an example. Let's represent events by just natural numbers. We have a sequential composition between two disjoint sets, one of which only has actions that occur later than all the actions of the other. So the sequential composition is just the direct union. And here we get an undefined one because we have the same number on both sides, and the not here rules that out, because the equal or less than is reflexive. So let's define a version of concurrent composition. It's done by just taking par as the union of the sequence operator, whatever it may be, and its converse. So par is just the reflexive closure of sec. And now we define P parallel Q in the same way by requiring everything to be in the parallel relation in order for it to be defined. It's easy to see that because par is itself commutative, the sequence will also be commutative, and the proof that it's associative is the same as the proof that sequencing was associative. And this exchange satisfies the exchange law with semicolon. Here are some examples, and the last one is perhaps interesting. It really shows you that interleaving is one of the ways of doing a parallel composition. That is a proof of the exchange law. And now I will come to my conclusion, if I may. What I'm interested in is working out theories that are going to be useful in the design of tools for software engineering. I don't expect real programmers ever to understand a theory as complicated as this, although perhaps they might learn it in their secondary schools one day. But tool builders really must agree on the semantics, the theory of the programs which their tools are operating on. I'm going to differentiate three kinds of tools. Verification tools, by which I will include program analysis tools, implementation tools like compilers and runtimes, and testing tools. And this is something which hitherto I have grossly neglected, although I believe that the testing tools are the things that will be the first to apply formal methods in general programming practice. Because testing is what programmers actually do already. And if you could make a 10% increase in the efficiency of testing by ordinary programmers, you would please them and their managers and their employers quite a lot. So testing tools, verification tools really require a deductive sort of logic, and the compilation tools and implementation tools really rely on an operational interpretation of programs, and testing tools depend on the models, the denotational semantics, the original Scott semantics, which tells you what the programs actually mean. And in my view, that I put forward to you, what they mean is the set of executions of that program. Because it's the executions that your testing tools are actually going to have to show to you and explain to you. And the sort of proofs that I've shown just simply show how you prove, in what sense those three types of tools can ensure their mutual consistency through the intermediary of the laws. The testing tools are describing how programs are actually, modeling how programs are actually executed, from which you can prove the laws, and then from the laws you can prove the validity of the two kinds of other semantics. So that's the big picture. Here's a summary of what I was hoping to say. The laws are useful. They tend to lead to short formulae, short theorems, and short proofs. They prove the consistency of proof rules or operational rules, if that's what you want. And they establish, the consistency with the implementations. I haven't shown you very much, but I've given just a start of how you would construct a model showing that and proving that the laws are true of the model. And I'm coming to believe that the laws are true not just of software, but of hardware. The laws are valid in models of, put it that way, hardware, software, and indeed the real world. Even in the real world, an event cannot happen if it depends on an event that has not yet happened. And violation of that principle would be, shall we say, run counter to thousands of years of scientific research. Might get you It might get your results published in the News of the World. No, sorry, that doesn't exist anymore. But it's not, as far as we know, good science. And the laws are beautiful? Well, I'll leave that to your judgment. Not everybody agrees with me. And the first person I'd like to quote who doesn't agree with me was Isaac Newton. Isaac Newton worked out beautiful laws for differential calculus. It's called the differential calculus these days. He called it fluxions. He wrote in a letter to Richard Gregory, our specious algebra, i.e. it looks convincing, but it's invalid. That is the infinitesimal calculus, is fit enough to find out. It has a heuristic value, suggesting what theorems there might be, but it's entirely unfit to consign to writing. You can't put it in your publications and commit it to posterity. I think posterity has taken a very different view. Bertrand Russell, in his introduction to mathematical philosophy, says, the method of postulation has many advantages. They are the same as the advantages of theft over honest toil. He put this remark rather carefully when he moved from a rather simple branch of the foundations of mathematics to one that really was quite a toil, going from integers to fractions. Gottfried Leibniz, 18th century German philosopher, had an one-word answer to both Newton and Russell: calculamus. Let us calculate, because algebra is the tool of calculation.